Okay, in this video, let's talk about the completeness of the CG omega. CG omega may not be complete if you just randomly get an open set and open set omega and open set G in whatever metric space. So first of all, it's a metric space. We already define a metric. Remember Q, the set of a rational number is a metric space, but it's not complete. Complete means every Cauchy sequence has a limit. Okay? So how do we know it may not be complete? For example, let omega be a non-complete metric space. If you have a non-complete metric space, then there is a Cauchy sequence Wn in omega which does not converge. Okay, so you have a non-convergent sequence, a non-convergent Cauchy sequence. And then we define Fn from G to the omega by f of z is equal to Wn, the constant function. All z in G. Then Fn in Cg omega is a Cauchy sequence. Because the distance between Fn and Fm is equal to the distance between Wn and Wm. So this is a Cauchy sequence. The Fn is a Cauchy sequence, but Fn, the sequence does not converge in Cg omega because Wn has no limit point, right? Okay, so this part we use the important property that omega is not, if omega is not complete. Okay, so when omega is not complete, we can definitely construct a non-convergent Cauchy sequence. But when omega is complete, from now on, we assume that omega is complete. Then we're going to prove proposition 1.12 that Cg omega is a complete metric space. Okay. Okay, so from this proposition and the previous example, we can see that the completeness of the Cg omega is totally determined by the completeness of the image set omega. Okay. So completeness is determined by the Cauchy sequence. So let Fn be a Cauchy sequence. And Cg omega, and Cj omega you have a Cauchy sequence. Uh, okay, now it means for any epsilon greater than 0, there exists a capital N such that for all nm greater than or equal to capital N, the distance, here we use this rho, the distance of Fn, Fm is less than epsilon. So this is the Cauchy sequence. Remember that when we have those epsilon, you can have that compact set K and the delta stuff, right? So we are looking, first of all, we have to find the limit. So we want to get the limit. So we are going to construct, we need to construct a continuous function f in this Cj omega with the limit of Fn is equal to f. So this is what we need to prove. And in order to construct the limit, so we need to know at least, not the sufficient, but necessary, at least the limit of Fn of z is equal to f of z. It has to be pointwise convergent. It has to be pointwise convergent. Okay? This is the minimum requirement. All right, let's see. So we need the compact set. So for each compact set, K in G and the doubt, right? You have the doubt. And for each compact set, we restrict Fn to K. So Fn becomes a continuous function from K to omega. It is still a Cauchy sequence. Okay, it's still a Cauchy sequence. Okay, let's see. For arbitrary delta greater than 0, there is an integer capital N such that the supremum of the distance between Fn of z, Fm of z in K is less than delta for nm greater than or equal to n. How do we get this? Remember, we have that important lemma 1.7. When you have a Cauchy sequence, it means this condition is satisfied. For every epsilon, you have this capital N with this property. And now we have a compact set K, and we have a doubt. K is fixed. For every doubt, for K delta this pair, you can find the epsilon. For the epsilon, you can find a capital N, so that when nm is greater than capital N, this distance between Fn and Fm. So you see here, this is the root. So from K delta, you get epsilon. This is lemma 1.7. From delta, you find the capital N. This is done by the definition of Cauchy sequence. Okay. You have this. And then the rho Fn Fm less than epsilon implies the supremum is less than delta uniformly on K, right? This is again the lemma 1.7. And in this process, the epsilon is hidden. You only see the capital N. You don't see the epsilon, but epsilon is necessary when you pass, when you try to find this capital. Otherwise, there's no way to find capital. Why this is correct? Okay, because Cauchy sequence. Remember, Cauchy sequence is determined by the distance. All right. Okay, so for each z in omega, for each z in omega, Fn of z is a Cauchy sequence. For each z in G, my bad, for each z in G, Fn of z is a Cauchy sequence in omega. Fn of z, it is always uniformly less than delta. Every delta you can find n so that the distance is less than delta. So it is a Cauchy sequence. When you have a Cauchy sequence, it has a limit. It is defined to be f of z. So this is our construction. We do find the limit based on the completeness of omega. Okay, so we have this limit. Now we constructed a function f. But this is just a function. We don't know if it is continuous, and we don't know if it is a limit of Fn. This is just pointwise definition. All right. So let's see. We're going to show it is continuous and it is limit. Okay, so for K, a compact set, and the delta greater than 0, fixed. So we fix the compact set, fixed delta. Then choose n such that this supermom distance Fn of z, Fm of z, z in K less than delta for all n m greater than or equal to n. All right. Okay, so for any z in K, for any z in K, you see the limit Fn of z is equal to f of z. So there is a sufficiently large let's use m. Let's put m here. There is a sufficiently large m such that the distance between fz and fm of z is less than delta. So this limit is less than delta. So be careful here. This capital N does not give us anything about the how far the sequence is from the limit. It just says they are close to each other. All right, and then here this m, it should be very, very big so that it's very close to the limit point. And of course we require here, we also require m is greater than or equal to capital N. So I want this is happen, this also happen. All right, so the distance between fn of z and f of z, by the triangle inequality, we know it's less than, so here the supremum is less than delta, here is less than delta, so it's less than twice of delta. For every point z in K, this distance is always less than twice of delta. And this works for all n greater than or equal to capital N. All n greater than or equal to capital N. Technically, you just let this approach infinity. You let m approach infinity. M is close to f, so here's n, here's m. Here's f, the limit. This is delta. This is delta, so this distance is less than 2 delta. Right? Okay. Okay, so what do we get? We get for any k, k is fixed, delta greater than 0, there exists n such that the supremum of the distance between fn of z, f of z, z in K is less than 2 delta, less than or less than equal to, it doesn't matter. And this implies that the sequence of fn converges to f uniformly on K. And K is arbitrary, right? For every delta you have this n, for a different delta you have different n, so it will converge to 0. Basically it will converge to 0 as the n approaches infinity. Okay? K is arbitrary, any K is arbitrary. And in particular, okay. So what does this mean? This just means if a sequence converges to f uniformly over whatever compact set, then the limit n approaches infinity, rho f fn will approach 0. And we only show that it's the element is close to the limit point, but we still don't know if the limit point is continuous or not. So we're going to show it is continuous. Here, for any for any point z in G, there is a r greater than 0 such that the ball centered at z with radius r is totally contained in G. It's totally contained. So the ball centered at z with radius 1/2 r and the closure is also totally contained in G, and it is compact. It's compact, and Fn converges to F uniformly on this compact set. And you can prove that all the Fn's are continuous. You can prove that F is continuous, right? You can prove F is continuous. So for Z, for this Z and Z prime in this open ball, the distance Z Fz prime is going to be less than the distance fz fn of fnz rho fnz fnz prime plus a rho fnz prime fz prime, correct? So remember, it is the uniform convergence. The convergence is uniform. It means for ZZ bar there exists n greater than 0 such that for n greater than or equal to capital N, the first and the third will be less than epsilon. This is less than epsilon. And the middle one, Fn is what? Is uniformly continuous. Fn is uniformly continuous. Because we're talking about a compact set, Fn is uniformly continuous. For the uniform continuous stuff, if the distance between z and the z prime is small enough, sufficiently small, delta, then the distance of fn of z, fn prime of z will be less than epsilon. Right? And okay, so be careful here. You first find capital N. And this capital N is uniform for whatever z and z prime. It does not depend on z and z prime. You have those two properties. And you pick up one Fn. You pick up one Fn. Fn is uniformly continuous. And then in this case, you choose this zz prime so that the distance is less than delta. This delta depends on this n. But you will get that the distance between fnz prime is less than epsilon. So the total thing will be less than 3 epsilon. It is less than 3 epsilon. So the f is continuous. Right? F is going to be continuous. So here the delta is really a function of n. For different selection of n, delta may be different. It's not uniform. There's no uniform stuff here. But for this zz prime, it doesn't matter how you select the zz prime. Here it's always uniform. Okay, so there's some orders here. So anyway, this is the here. This is the argument in the textbook. In particular, the convergence is uniform. Uniform. Okay, so this argument explains. It appears on page what is it, 146. It says this gives theorem chapter 2 section 6.1 that f is continuous at each point. So why it is continuous, you go through this, you get it. So what we get f is continuous, and where is it, and the distance between f and fn is becomes 0. So this Cauchy sequence converges to f in Cj omega. So Cj omega is complete. All right. So we do prove that Cj omega is a complete metric space. And in this part, we use the completeness of omega because whenever you have here, whenever you have a Cauchy sequence fnz, it always have a limit in the omega. So this place we use a convergence. All right. So next, let's see a classical notation, the definition. The definition says a set f in Cg omega is normal if each sequence in F has a subsequence which converges to a function f in Cg omega. Okay, this is normal. The definition of the normal family. It's called normal family. Well, this definition is not the sequential compact subset definition. Okay, so this is not the definition of sequentially compact subset. Sequentially compact subset. Because sequentially compact subset will require that every sequence has a convergent subsequence to itself, inside itself. But here we don't require F to be in family F, which only require F to be in the superset Cg omega. Okay, be careful. This normal family is not the sequentially compact. Well, it's not it, but it's very close to it. So the obvious proposition is that a set F in Cg omega is normal if and only if its closure is compact. Its closure is compact. Alright, you take closure, it becomes compact, then this is a sequential compact. We put closure to include the limit points. Alright, so try to prove it, write it down. There's some sentences you need to make it clear. Okay, but it's not difficult. It's just a play of a language. Well, next, let's try to use compact subset and the delta language to rewrite the normal family. So normal family is defined by the sequence of elements and subsequence convergence, and this is related to the metric. Now let's try to use that compact subset K and the delta to rewrite the normal family. A set F in Cg omega is normal if and only if for every compact set K in G and delta greater than 0, there are functions f1 up to fn in F such that for element F in the family F, there is at least one k is between 1 and n with the supermum of distance fz fk of z in compact set k is less than delta. Okay. It's always included in this. So that's another way to rewrite this normal family in terms of a compact subset and the delta. Okay, so there are two directions. So we have to prove two parts. Proof. Suppose F is a normal family. F is normal family. So from here to prove the other one, we're going to prove this. And it says for every compact subset K and delta, and let K and delta be given. Okay, so whenever you have a K and a delta, there is an epsilon greater than 0, such that the lemma 1.7. Whenever the distance between Fg is less than delta, it will imply the supermum distance Fz Gz z in k less than delta. Right? So we always have this. This is 1.7. F is normal. Then F closure is compact. F is normal, F closure is compact. If you go back to page 22, the theorem 4.9. In the theorem 4.9, you will have 4 equivalent statements about the compact set in the metric space. There are 4 equivalent statements of compact subset in metric spaces. Okay, so you have to review this part. And one of them, part A and part D. A means K is compact. D means X is compact. Part 1, X is compact. Part D, it says X is complete. They are equivalent. And for every epsilon greater than 0, there are a finite number of points x sub 1 up to x sub n in X such that the X is the union of a ball centered at X sub k with epsilon, radius epsilon. K is from 1 to n. And this property is called the total boundedness, not complete, only the other part is called total boundedness. Okay, for every epsilon you can find the x1 up to xn, so that x is a union of balls. It's a total boundedness. Okay, so we're going to use this total boundedness. So F bar is compact, so F bar is totally bounded. F bar is totally bounded. F is totally bounded. Okay, so the thing is that when you choose x1, x sub 1 up to x sub n in X, for example, you choose when you talk about F bar total boundedness, you choose F1, Fn in F bar. But when you talk about the F totally bounded, you need to modify your selection so that this finite family belong to the F, not F bar. So you have to move a little bit, but it's not difficult because this is closure. Whenever you have a point here, you will have another point very close to F1, another point very close to Fn. Okay, so try to make this write down your argument. Okay, so here we assume F is totally bounded. F is totally bounded, then you see you already have epsilon. You already have this epsilon. For every epsilon, this means for every epsilon, so this epsilon is selected. So for this epsilon, there are F1, Fn in F such that F is contained, is covered by the it's covered by those open disks. So here bxk epsilon in this part we write like this. This is exactly the ball. And this will imply this part. This implies F belongs to the union of k from 1 to n. Well, it's not that. It's a supermem. It's this. F, then the supermem of those distances between Fn, k, z in k, this less than delta. So all the F with those properties. Okay. See, so So this is exactly the statement for every element F, because this family is covered by those unions. So whenever you choose F, F will belong to one of them. One of them means it will satisfy one of those conditions. Right? So we get one direction. The other direction. So this direction is totally depend on this total boundedness. It's another total boundedness is like that open cover has a finite subcover. We try to feel that open cover has finite subcover, but we just use a metric language to rewrite it. Okay, so the converse. For the converse, suppose that F has the stated property. What is a stated property? Stated property just means it is this condition is satisfied. Just means this property is satisfied. For every compact set K, you can always find this. All right. So we only need to show that F bar satisfy the condition or satisfy the statement. Satisfy the statement. Okay, so here what do I mean? We only need to show that F bar satisfy the statement. So if F bar has this property, and we prove that F bar is compact, then F bar F is not. Right? If we have this property and we show F bar is compact, then F becomes normal. And this one, it is inside the union of open set. Then of course, closure of F bar also contained in the union of them. The closure also contained in this union, right? So now we will just talk about F bar. To talk about F bar, we mean F is closed. So assume F is closed. We don't assume it. Let's not assume it. So F bar is closed. CG omega is complete. Then F bar is complete. Every closed subset in the complete metric space is also complete. Okay? And F bar with this property is totally bounded. Why? F bar with this property is totally bounded. It's because For every k and the delta, f satisfy this condition, then f bar also satisfy this condition. It is covered by the open disks, and those f, they belong to the family, they also belong to the closure of the family. So this is exactly the definition of the total boundedness for f bar. But without the closure, we cannot claim it is complete. With the closure, we can say it is complete. Okay? Okay, so it's complete total bounded. So f bar is compact. F bar is compact. F is normal. Right? So the normal family is just one step away from the compact set. Whenever you want to discuss the normal family, you may consider its closure, its compact closure. All right, so that will give you the easy part. And the compactness has some this is theorem 4.9 has some equivalent statement for the metric spaces. Okay, so this is the discussion of a normal family, and the next we are going to prove or present Asela-Ascoli theorem. We'll finish it. So, Asela-Ascoli theorem. We're going to present Asela-Ascoli theorem, and it will take possibly one video. Okay, so we stop this video and we will continue on next video. Thank you.